but I'm still recording. Remind myself how silly I look. There it is. So I don't know how you guys take me seriously all day today when I look like this, and I gotta stare at myself. Anyway, average rate of change, the definition of derivative. So this whole unit is sort of intro to derivatives. And we'll start with average rate of change, and I believe that was the bonus question on the test. That almost, I think one person got it right, and one person I gave some partial credit to because they were close.
It's always the average.
Ish. Average rate of change. We asked you that a bunch of times last year in pre-cal, but the average rate of change, and a lot of times we'll just abbreviate it AROC, is simply the algebra slope. So average rate of change might be a new name. It shouldn't be. You should remember it from pre-cal, but the formula, the concept is algebra 1, right? Just good old slope. y2 minus y1 over x2 minus x1. We'll make it look a little bit fancier with function notation. So f of b minus f of a over b minus a. But really, if you'll remember that AROC means algebra slope. The A's kind of go together. Because we're going to look at a different kind of rate of change in a few minutes. That's not algebra, that's calculus. But, well, let's start with average rate of change. So let's find the average rate of change of f of x equals 4x squared minus 9 from negative 1 to 3. So I got my x values. Let's find f of x. So f of negative 1 and f of 3. If I plug in negative 1, 4 minus 9 is negative 5. F of 3. 9 times 4 is 36. 36 minus 9 is 27. And then which one you call A and which one you call B, which one you call X1 and X2 don't really matter as long as you keep things straight. So I'm going to go 27 minus negative 5, because that's the Y values, over the X values in the same order, 3 minus negative 1. And by the way, as weird as that looks, that would be a safe stop. You could just stop there and be done. Now, multiple choice test, it'll keep going. 32 over 4 is 8. But any of those would be a fair enough safe stop. Meaning you don't have to go any further than that. In fact, you probably shouldn't go any further than that, because what if you mess up and you think 27 minus negative 5 is 22, or you mess up the signs. If you're done with calculus, if all you have left is add, subtract, multiply, divide stuff, then leave it and be done. Save you a little time and probably saves you points. All right, for time purposes, I'll skip example 2. It's the same stuff. You need to know the sign, but you can look that up if you don't know the unit circle. Definition of derivative. Okay, so we're going to get to the definition, but let's talk about what a derivative is before we get to the formal definition, or what it tells us. It tells us the slope at a point, which is weird because the slope formula always has 2 points. So how in the world are you supposed to find the slope at one single point? That's the whole point of the first semester.
Pun intended?
Yes. Slope of a tangent line. That's another way we phrase it. Let's just put so there's a tangent line. The slope of that tangent line is the same thing as the derivative at that point. Another name for it is the instantaneous rate of change. Instantaneous rate of change. So the AROC is the algebra rate of change, or the average rate of change. The IROC is the calculus rate of change, the instantaneous rate of change. What's happening at that one point? And you can see why good old algebra won't work here, because algebra, you got to have 2 points, and here there's not 2 points to mess with, so you're kind of stuck. But the definition of derivative comes from algebra. So let's draw a little bit better picture of basically the same thing. And let's say we want to find the slope at that point. Well, we don't know derivatives yet, so let's just pick another point over here and we'll get the slope of this line and say that's as good as we can get for now. And we're going to say that the distance from the point we're worried about to the next point over that we're going to use to find slope is delta x. Delta means change, so that little bitty amount is how much x has changed. Well, the slope formula needs some y values. So f of x. And the other one would be f of x plus delta x. That's x plus delta x in there. And so let's find, I'm not pulling a popsicle stick yet, I'm just doing a straight edge. Let's find the slope of this line to start with. So that's not a tangent line, that's not an instantaneous rate of change, that's not a calculus slope, but it's a place to start because it's an algebra slope. So we can do the algebra slope of that line. So y2 minus y1, f of x plus delta x minus f of x all over x plus delta x minus x. That would be the slope of that line. And by the way, that line is called a secant line. I don't know where that name came from, but secant and tangent, they're both trig functions. They don't. Tangent line's what we want, because that's what this is. That's a tangent line, and that's what we want to find the slope of. But right now, the best we can do is this secant line. We can clean up the denominator. I can't really do anything with the numerator because I can't distribute that f. I don't know what f is, so I probably can't just distribute it. I'm just going to leave it as x plus delta x minus f of x all over, let's see, delta x. Which, now looking at it, I hope makes sense. It's the change, slope is the change in y over the change in x. So we don't have the change in y labeled, but we already have the change in x labeled, so that's the formula for our slope. In fact, we could just pause here to say that's the that's the average rate of change. That's the algebra slope. So we have not done any calculus yet. That's all algebra. I mean, fancy letters maybe with the delta x and fancy names, secant line, but that's all algebra. You good with that? I mean, that's good. Good old slope formula. y2 minus y1 over x2 minus x1. Now, if we want our secant line to be closer to our tangent line, so if we wanted this to be like a good approximation of the tangent line, what value, like on my picture, would I need to change, and how would I need to change it so that my secant line became more like my tangent line? Yeah, if my delta x was smaller, there's the tangent line that I want. If delta x was small, like really small, then my secant line would approach my tangent line. Right? Does that make sense? Like the smaller the step, the closer the line is, the secant line is to the actual tangent line. Yes, no?
Yes.
Anybody else? Yes, no? Give me some head nods. You can say no. Right, well, here comes the calculus. So if we want delta x to be small, really small at that, let's take the limit as delta x goes to 0. Because if delta x goes to 0, then our secant line turns into our tangent line. And that's what we want. And in fact, that is the definition of a derivative. That's f prime. So when we say use a definition to find a derivative, that's what we mean. And in fact, another way to say that is that's the instantaneous rate of change. Yes, sir?
What's delta of x?
It's the space between the two points for our slope. It's just the measure of how far that is. And we want it to get smaller and smaller and smaller so that our secant line becomes our tangent line. So that's one of the big deals for today. We'll do another one in just a minute. Oops, I should have highlighted the whole thing. That's the definition of a derivative. You have to know that moving forward. You just got to know that. But we go through all of that, so hopefully it's not just a straight memorized thing, but you realize that it's just a slope formula. Like there's a lot of new letters in there, and you haven't seen that before, but we want you to realize it's just a slope formula, where if I let the denominator get really small, then instead of a secant line, I have a tangent line. So our hope is for understanding, not just memorizing. The AP test will ask questions that test your understanding, not just, oh, did you memorize it and can you plug some stuff in? So I hope that makes some sense about the connection between the average rate of change, that's the secant line, or the slope of the secant line. The tangent line is the instantaneous rate of change. Right, let's turn the page. There it is again, nice and spelled out, typed up neatly in case your handwriting wasn't great. The definition of the derivative of a function is limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x. But again, it's the slope formula. With the small delta x, a really small delta x, like nearing 0 delta x. All right, lots of different notations that all mean the same thing. We use different notations for the derivative of a function. Kind of depends on the situation, and they're not entirely interchangeable, but for the most part, they're interchangeable. And throughout the year, I'll try to use all of them, just mixing them up just to make sure we stay familiar with all of them, rather than like sticking with one the whole year. We're going to try to change them up. So the derivative of y with respect to x can be written as d dx of y. That sort of means take a derivative of y. dy dx, that's sort of the same thing. And then there's the prime notation. Y prime or y prime with parentheses x. The derivative of f with respect to x, well, just replace all the y's with f. Replace the y with f. Replace the y with f. Replace the y with f. And usually y and f are interchangeable, so there's at least 8 different ways to say derivative. In addition to other ways to say it, other names. Slope of a tangent line, or instantaneous rate of change. So all of those mean the same thing. And again, we try to mix it up so that you get used to seeing all of them. All right, given g of x equals 3x squared minus 2x, find g prime of x. So g prime of x, we're going to use this definition up here. So if I want to use that definition, I need g of x, I need g of x plus delta x, and delta x is just a variable. All right, so let's find, like I'm aiming for this equation, so I need all the pieces that go in this equation. Again, g of x we know. We don't know g of x plus delta x, so we're going to have to take the time to find that. Well, I hope this is old news. This is what we're doing in pre-cal right now. Right, whatever's in parentheses goes in for x on the other side. So my input is now x plus delta x. And we'll square it. Minus 2 times x plus delta x. Okay, this is going to get a little ugly, but I need to do the ugly and see what happens here. Hopefully you can FOIL that without having to write it all out, but if you need to write it all out, by all means, write it all out. X squared. And if I FOIL it, surely we know we're not just going to square the pieces. I'm going to end up with 2, the middle terms, outside and inside, x times delta x plus delta x squared.
Would it be x plus delta x or x times delta x for the 2?
Times. Those are all times. And then distribute to negative 2. That's the easy part. And I guess if I was really paying attention and really comfortable with squaring that funky looking thing, I could have distributed the 3 all in one step. But that's our first one, so slow it down a little bit. Calculus is easy, algebra is hard example here. Okay, so all that work, and it's like now I'm sort of ready to work the problem. That was all lead up, because now I know what f of, or g of x plus delta x is.
Yummy.
It's all of that stuff. So 3x squared plus 6x delta x plus 3 delta x squared minus 2x minus 2 delta x. All of that. Minus g of x, yep, minus g of x is 3x squared minus 2x all over
delta
delta x. And I'm trying to find the limit as delta x goes to 0.
My brain
And
hurts a little.
even without cleaning up the top, we're going to need to clean up the top. What's the problem here?
Not all of them have delta x's.
Even before that, looking just at the denominator, what's going to be the problem?
It's going to be over 0.
It's going to be a 0 in the bottom. So that either means infinity, or it means, hopefully it means something can reduce and we can get an actual number here. So let's clean up the top and see what happens. For polynomials, everything in the g of x should cancel. So minus 3x squared and a plus 3x squared goes away. What about minus 2x and minus 2x? Those cancel?
Minus
That was-
2 and plus 2.
That's a misleading question, right? Why will they cancel?
Because you're subtracting a negative.
Yeah, if I distribute the negative, then we're good. So, hopefully that's not a spot where you need to write out the whole line to distribute a negative sign. I think that's all. That's it for all the like terms.
Mm-hmm.
Once we've done this enough, some of you are going to jump from here to the answer. I'm going to say not yet, because I want to make sure my algebra is good. So I'm going to rewrite what's left. Just trying to keep things nice and neat here. And the problem was that delta x in the bottom. Yeah, it's 0. Will it cancel though?
Yes.
Yeah, there's a delta x in everything in the top. So this is good news. So 6x plus 3 delta x, right? Because there are 2 of them and one of them goes away. Minus 2. Okay, so one of our algebra magic tricks worked. Delta x in the denominator went away. It's still in the numerator, but I don't care if it's in the numerator. I just couldn't have it in the denominator. All right, so limits. Back to limits. Substitution first. Rarely works. It didn't work here, or wouldn't have worked here if we'd have tried it. Do some algebra tricks. Let's substitute again. Well, this is pretty easy at this point. If I plug in delta x equals 0,
6x minus 2.
I get 6x minus 2. And so that is my answer. That's the derivative of g at any particular x. So if I want to know the slope at any particular point of x, I just plug in 2 or 7 or 12 or whatever point I want to know the slope at. I've got this formula that tells me the slope of g at any x value, let's say. Because I can plug in the x value if I want to know the slope at 10 or at negative 3.
This is kind of tedious.
It is. It is a little bit tedious.
I vaguely remember a shortcut.
A shortcut is coming, but not till Monday.
Ah.
So you have to live all weekend without a shortcut. Keeping an eye on the time, we're fine. Example 2. Fraction.
Yep.
Find dy dx. So we've used a different notation, but it's still the same thing. We want to find y prime of x. So those are all the same thing. So again, I need to find y of x plus delta x. Well, I guess this is the pay me now or pay me later situation. Or more specifically, it's a pay me later situation. Because the pay me now is easy, like plugging in for x with x plus delta x, that's pretty easy. The hard part's going to come when we shove it all into the definition of a derivative.
Which
Y
is right
prime
now.
equals the limit as delta x goes to 0 of, so there's y of x plus delta x minus x plus 1 all over delta x.
Do we have to the reciprocal or?
Not the
No, the
reciprocal, but we are going to have to
bottom
fix it.
What?
Common denominator.
Yeah, the bottom fraction.
Okay, I lost.
Because if I plug in a delta x now, or if I plug in 0 for delta x, I get 0 in the top and 0 in the bottom. So, yuck, I'm stuck. Until I multiply top and bottom by what will be a common denominator.
Or the little denominators.
It's ugly, but it's really not that bad, because in the denominator we just leave all that stuff there and hope something cancels out.
Yeah.
I'm lost.
In the numerator, we're going to have to distribute and see what cancels, and we'll have to do a little work. But the whole point was to make the denominators go away. So the top looks bad, but it's going to turn out to be pretty simple. Easy for me to say, I guess. Limit as delta x goes to 0. So if I distribute this whole chunk of two denominators to this first term, I mean, it looks awful, but the worst offenders cancel out, right? All of that cancels with all of that, and we're left with x plus 1. So that wasn't too bad. Minus
X plus delta x plus 1.
the second one, the x plus 1's cancel. And let's be careful with that minus sign, make sure it gets to everybody. X plus delta x plus 1. All over, and then this is a mess, but we're not multiplying it out. We're just going to leave it as is. And if someone cancels out the x plus 1's, I will throw something at you. That is not okay, algebra. We need to clean up the top and then see what will cancel. So let's see. Oh, we've got things going away again. So x minus x will go away. 1 minus 1 will go away. And be careful, that minus sign is still there. So negative delta x over our monstrosity of a denominator down there. No, I just did what I was going to try not to do.
What'd you do?
Officially, you're supposed to write the limit statement every time. Most of the time, students are like, look, I got 8 awful algebra steps to go. Why do I got to be writing the limit statement every time?
Because they can take off points.
Officially, you're supposed to write it. AP test, you should write it. In here, as long as you remember to put it on at the end, if you write this, I know what you mean, you'll be okay. Let's see, the delta x's will cancel. So I've got negative 1 over x plus delta x plus 1 times x plus 1. I think we're finally ready to do another attempt at substitution. Yeah, if you do all the algebra right, that's a big if. If you do it all right, when you get to the second attempt at substitution, things go pretty well. Because if I plug in 0 for delta x, I think that just goes away, and I'm left with negative 1 over, well, I got 2 of them, so I'm just going to write it as x plus 1 squared.
And that's y prime.
And that's y prime, or y prime of x, or, oh, I guess they originally called it dy dx, so maybe I should call it that. But if you use them interchangeably, I'm not going to take off for that, because they mean the same thing.
With AP?
Nope, they'd be okay. Yeah, there's far more difficult things for them to worry about than what you called it, as long as you called it something accurate. Okay, so that's ugly. A shortcut is coming, but, and you'll see this in today's homework, there are ways we ask the question that force you to be able to do the definition route rather than the shortcut route. All right, alternative form of a definition. Back up, because I need to contrast definition versus alternative form so that you know when to use each one. So back up to the original definition. The definition gives you the slope for any x value. If you look at the two answers that we got, they had an x in them, so that they're useful for any x that you want. Right? Once you have that formula, you can plug in 2 or 7 or negative 5 and find the slope at that point. As opposed to the alternative form of the definition, it gives you the slope at one particular point, at one spot. So here's the trade-off. Like, that's not as helpful, right? Because if you do the full definition, you've got a formula you can use for any point. If you use this definition, you get one answer, and one answer only. Now, a bit of the trade-off is this formula is easier, but it only gives you one answer. So it kind of depends on the situation of, well, do you want to use the alternative form and get your one answer, even though it's quicker, or do you want to use the full definition and get a much sort of stronger answer, but it's a little bit more difficult? Basically, you don't usually have to make the decision. We'll make the decision for you and ask you to use whichever one we want you to use. All right, another picture. You know what? Let's do a negative slope here. And let's say we want to find the slope at A. So again, we'd really like to find the slope of that tangent line. This picture is going to be really similar to the last picture, where we're going to get a algebra slope, shrink the denominator to 0 to come up with a calculus slope. So we're aiming for the slope at A. Let's pick some other point over here, x. So that would make, if we use those 2 points, a secant line. So let's start with the good old algebra rate of change, average rate of change. I use those terms interchangeably. There's no such thing as algebra rate of change, but if I say it that way, it helps people remember what we're doing. Algebra rate of change, I'm going to do f of x minus f of a all over x minus a. That's my algebra rate of change. On the last picture, you said let's shrink delta x to get a smaller denominator and to get our tangent line closer to our secant line. Very similar here. If I want an instantaneous rate of change, I would really like this x to get closer to a. Right, that'd be nice. The closer x is to a, the better my approximation is. And if x goes toward a, you can't really get there, because if it gets there, we're dividing by 0. That's the whole limit thing. Yeah. As it gets closer to a, my numerator and denominator are still the same, but my overall slope is a more accurate slope, and it's the derivative at a. So it's a little bit easier formula, but it only works for 1 point. So, which one? We'll tell you which one to use. All right, example 1. Find f prime at 2 given f of x equals that. So if we want it at 2, that means like 2 is our a value here. So a is equal to 2 in that example. So I'm looking at my formula. F of x I know. X I know, because x is just a variable. A I know. I need to find f of a, which is f of 2. So we plug in 2. Let's see. 2 times 4 is 8. Plus 8 minus 3 is 13. So now we're ready to use the formula. Limit as x approaches a. Please at least write it once. I know there's more work to do and sometimes you'll leave it off. That's fine. Write it at the start, write it at the end, and I'll assume you can assume I'll visualize it all the rest of the time. And then minus 13 all over x minus 2. Oh, there's one small thing that I messed up there. It's not really wrong, it's just not clear right now. Because I know what a is, so I don't want x approaches a, I want x approaches 2. Although it wouldn't be wrong to write x approaches a because I told the grader that a equals 2. So it would not have been wrong, just a little more.
Your point.
So let's clean up the top. I'm guessing if I plug 2 in now, well, I know I get 0 in the bottom. I'm guessing I get 0 in the top as well. So let's factor the top and hope that something cancels. And I was worried this was going to be one of those yucky factoring where you have a lead coefficient of 2 and you got to really play with things. But it's not, because we could take a 2 out of everybody. And you see I've dropped my limit statement. Let's see, factor that. I hope x minus 2 is one of the factors. And it is. So the x minus 2's go away. What do you think we do next?
Plug it in.
Plug the 2 in. So 2 times 2 plus 4. That's my answer. 2 times 2 plus 4. That's an okay answer. That's a safe stop answer. Let's see. 6 times 2 is 12. So I don't even want to say 12 is a better answer. 12 is what the multiple choice answer would be. 2 times 2 plus 4 would be a safe stop answer. So as we go through the year, you'll get used to me writing sort of both forms. And because it kind of depends on multiple choice tests, you need to be able to algebra your way all the way to the end. But if it's a free response question, don't risk messing it up. Leave it alone. That way you don't lose a point for something silly. All right, I'll leave example 2 for you to do if you want to do it. Today's assignment is, you don't have today's assignment, is worksheet 1 in the packet.